Okay, so the next thing I wanted to talk about with the exponential functions and derivatives of them is the inverse of the exponential function, which is the logarithmic function. Now, I think sometimes the notation here throws people a little bit, but I want to connect it back to what you did in advanced functions. So last semester, you guys did something that maybe you had log base 2 of 8. You knew that that meant 2 to some exponent gave you 8. Okay, and we had functions where we would say f at x equals log base 2 of x. And we know that this was the inverse of the function 2 to the exponent x. Okay. Remember also that there was a kind of logarithm that we did that was so common that we actually didn't bother writing a base. And that was the log base 10. So last year, if we had something that we just said log 7, we knew that that was equivalent to saying log base 10 of 7. We use that base 10 so often that we kind of short form it and say if we just write a log and we don't put a base, we just all know that it's 10. So now that you guys have seen that the exponential function with a base e is such an important function in math because it's the only one where the derivative is actually equal to the function itself, there's also an important function where it's the inverse of that, which is the log base e. So just like these ones up here, if we had log base e of x, we kind of want to get a short form notation, very similar to how we don't write the base 10, just to kind of make the notation easier because 10 is so common. Well, it turns out that base e is actually more common than base 10, and it's particularly common in modeling natural growth rates in a lot of scientific applications and in a lot of things that happen in the natural world. So because of that, we call it the natural logarithm, and it's shortened to ln for logarithm natural. So like the natural logarithm, if you see this ln with no base, all it means is that it's the log base e. And I know sometimes that notation is a little bit tricky. It's pronounced ln, which I know doesn't maybe seem like what it would be pronounced like with the ln. I've heard a lot of different attempts at reading ln out, but what this is just very much the same as if you say log with no base, we know it's base 10. If you say ln or ln with no base, we know it's base e. So going back to what I talked about before, if we looked at the logarithmic function, which we know is the inverse of the exponential function. So I'm just going to kind of very super roughly, no scale, just to get the shape of this function. Think about what this would look like. Now, this is going to have a positive slope for the whole function. So the derivative is going to always be positive. As we get really close into 0, we see that the slope of the tangent is really big positive. It's going to get steeper and steeper the closer you get into 0. So the y value of the derivative, or the value of the f prime at x here, will get larger and larger positive as you get closer to 0. So it's going to go very big positive as you get closer to 0. Okay, and then the slope will still be positive all the way along here, but it's kind of leveling off and it's going to flatten out. So we start with a very large positive number with going up to an asymptote at 0. It gets so steep, and then it's going to decrease and kind of come down and level off, but it'll never go into the negative. So it has an asymptote at the y-axis and also at the x-axis. It's always going to have a positive value, but it's decreasing. So the slope here is always positive on my original function. I'm going to label that as the derivative. The slope of my original function is always positive, but it's very big positive close to 0 and decreasing as the x value gets larger. So what that derivative function actually really looks like is one of the functions that I drew in the last video is the reciprocal function. It's the 1 over x. And that actually is the derivative. So if f at x equals ln x, or the natural logarithm of x, then the derivative of that function is 1 over x. There's one other derivative that you guys are going to be responsible for, and that's a general function where you have a function that is an exponential with a different base. So it's some other base than e to the exponent x. And if you remember in the last video, I said that it's still going to have an exponential function as its derivative, but it's going to have a scalar multiple. And the scalar multiple that ends up being, which the proof of this is a little bit beyond what we're going to be responsible for, the scalar multiple of that is actually, so if g prime at x is going to be this same exponential function multiplied by the natural logarithm of the base. And that's the scalar multiple that is the stretch or compression factor on the original function that gives you the derivative. So I'm also going to post up a list of summary of all of the derivative rules for these, and I'm going to do a couple examples of how to calculate the derivatives of these functions.